cheese, ready to be cut up and served in little squares. Does the total mass of the cheese change depending on how you dice it up? More optimistically, can you get more cheese by cutting it in a special way? Common sense says obviously not, but mathematically, the answer is not at all obvious. In fact, the mathematical answer is called Fubini's theorem. This major result is foundational for integral calculus in higher dimensions. However, even in 2 dimensions, this theorem has a tricky statement which can be difficult to unpack. In this video, you will learn to interpret Fubini's theorem in 2-dimensional space by cutting a flat sheet of cheese in different ways. Let's describe the question in more formal mathematical terms. Let R be a rectangle in 2-dimensional space. Let phi be a bounded, real-valued function on the rectangle R. There are 3 kinds of so-called double integrals. The first kind is the 2-dimensional integral, sometimes called the Darboux integral or Riemann integral. This is defined with partitions of R and upper sums and lower sums. The other 2 kinds are called iterated double integrals, defined using 2 one-dimensional integrals. These are sometimes called the dy dx integral and the dx dy integral, based on the order of integration. Before continuing this video, make sure you have had some introduction to these formal definitions. Now, when do these integrals exist, and when are they equal? Surprisingly, one of them can exist while the other 2 do not. We are not so concerned with these kinds of counterexamples. Fubini's theorem, on the other hand, describes when these integrals do exist and are equal. Our goal is to interpret this theorem in terms of our cheese. Our cheese rectangle can be viewed as a subset of 2-dimensional space. Along the x-axis, it ranges from x equals a to x equals b. Along the y-axis, it ranges from y equals c to y equals d. The cheese is the rectangle R defined as the Cartesian product of the interval AB with the interval CD. What corresponds to the bounded real-valued function phi on the rectangle R? Consider a point xy on the cheese. You can interpret the value of phi of xy as the density of the cheese at the point. So this will vary throughout the space. Mathematically speaking, the function phi may take negative values, but for the sake of this cheese analogy, it is better to think of phi as non-negative. With this correspondence between the math and the cheese, we can start to unravel Fubini's theorem. Let's begin with the setup of Fubini's theorem in 2-dimensional space. We will focus on the dy dx version. The dx dy version will be similar. Let R be a rectangle in 2 dimensions. Let phi be a bounded real-valued functions on the rectangle R. The theorem is an if-then statement with more setup, several assumptions, and a conclusion. Right now, let's focus on the first assumption. Assume phi is integrable on R. In other words, the 2-dimensional Darboux integral of phi over the rectangle R exists. We have already seen how the rectangle and the function correspond to the cheese and its density. How can we also interpret this first assumption and double integral? Remember, phi of xy represents the mass density of the cheese at the point xy. The 2-dimensional Darboux integral corresponds to the actual definition for the mass of the cheese. You can think of this as the mass of the cheese measured all at once. For example, I can measure its mass with a scale. The mass is 60 grams, so the integral is equal to 60 grams. This explains how to think about this aspect of Fubini's theorem. For the next aspect, we will reveal more setup. For x in the interval from a to b, define the x slice of phi to be the single variable real-valued function with domain CD mapping y to phi of xy for all y in the interval from c to d. Notice the function phi superscript x is called the x slice of phi. It is defined with the value of x fixed. This means each value of x gives a new one-variable function on the interval from c to d. So there are infinitely many x slices of phi. Let's bounce back to the cheese. An x slice corresponds to fixing a specific value of x and cutting an infinitesimally thin slice of cheese, dx. As a side note, I will not use the word infinitesimal in a rigorous way. But you can think of it as infinitely thin. In any case, I cannot actually cut an infinitesimally thin slice of cheese, so I will cut them into pieces with small width. Think of the width of this x slice as dx. Now, remember, the x slice is a function of one variable, namely y. So I need to transport this slice from the two-dimensional xy plane to the one-dimensional y-axis. So remember, x is fixed, and everything is now one-dimensional, ranging from y equals c to y equals d. For any given value of y, the density of this x slice at y is equal to phi superscript of y, or in other words, phi of xy. This wraps up how to interpret the x slice. We are ready to reveal the second assumption. Fubini's theorem also assumes that the x slice of phi is integrable on the interval from c to d for every fixed value of x in the interval from a to b. In other words, the one-dimensional integral of phi of xy from y equals c to y equals d exists for every fixed value of x in AB. What does this mean in terms of cheese? Remember, for the x slice of phi, the value of phi of xy corresponds to the mass density at the value y. So, the integrability of the x slice on the interval from c to d means that its mass can be computed as a one-dimensional integral of this density. This corresponds to chopping up the slice in many small pieces with infinitesimal length, dy. This piece of the x slice has density phi of xy. It has length dy and width dx. So its infinitesimal mass is phi of xy times dy times dx. Totaling up the contribution of these little cubes, I must integrate along the y-axis to get the integral from c to d of phi of xy dy, all of that times dx. This expression corresponds to the infinitesimal mass of our fixed x slice. Notice the integral dy corresponds precisely to the newest assumption in Fubini's theorem. You can interpret this integral as the density of the x slice itself. Finally, the conclusion you've been waiting for. Assuming phi is integrable on the rectangle, and all the x slices of phi are integrable on the interval from c to d, Fubini's theorem shows that the double iterated integral dy dx exists and equals the integral of phi on R. Magic. But How can you interpret the dy dx integral? Let's transport this one-dimensional slice back to 2 dimensions. Recall how this single x slice has infinitesimal mass given by the integral expression, the integral of phi of xy from c to d, dy, all of that times dx. And this was achieved by chopping up the x slice along y. We can repeat this process for all the other x slices. Instead of chopping them slice by slice, I'll save time by chopping it all at once. Different values of x will have different values for this infinitesimal mass. Totaling up all of these slices dx corresponds exactly to the dy dx integral. In other words, the total mass of these little cubes will be the same as the mass from before. Voila! 60 grams. I took something obvious, made it complicated and not obvious, and again concluded the obvious. That's one of the many miracles of mathematics. Revisiting our original questions, we have settled the problem for the dy dx integral with a version of Fubini's theorem. The same can be done for the dx dy version, but the theorem and the chopping are a bit different. Here is the old dy dx version, again, of Fubini's theorem. Now here is the new dx dy version. This was rewritten fairly easily by simply swapping the roles of x and y. The x slices are now y slices, and the iterated integral is now dx dy. The formal statement looks the same, but the geometry of the cheese is different. Let's compare the dy dx chopping with the dx dy chopping side by side. Both sides start with the same piece of cheese. The mass is the same 2-dimensional Darboux integral for both. Each side is chopped differently. One is first vertical, and the other is first horizontal. The dy dx version first uses x slices, so it is chopped dx, which means vertically. The dx dy version first uses y slices, so it is chopped dy, which means horizontally. We chop the second slice accordingly. The left one dy, so horizontally, and the right one dx, so vertically. A single cube has infinitesimal mass written as phi of xy dy dx or phi of xy dx dy. Totaling these cubes along the corresponding axis, we get the infinitesimal mass of each slice as a one-dimensional integral. Now, totaling these one-dimensional integrals gives the corresponding iterated double integrals, and these should equal the total mass of the cheese, 60 grams. This illustrates how Fubini's theorem says that the total mass of cheese does not change no matter how you dice it. On the bright side, this also means you don't lose any cheese. It's all Gouda.